So three metrics we have defined. One is a rotation, which is 2 by 2 matrix. Translation is 1 by 2 matrix, and we have scaling matrix is 2 by 2. So you need to observe that by combining all the transformation into the resultant transformation system, a homogeneous coordinate system you have to use. Suppose following the sequence of transformation is required to be carried out. First is rotation about origin, second is the translation, third is the scaling, and if P is a row matrix x and y, P prime is x prime, y prime is a row matrix of the coordinate of the final transform point. The first operation you have to do is the rotation about the origin. So originally we have matrix is P and we have to do the rotation about the origin. In that case, the first matrix form is P1 is equal to matrix P multiplied by R. Then we want to carry out the translation. In the translation, we have to obtain the value of P2 as rotation plus we have a translation matrix T. Scaling is obtained by multiplication and we get the final point P prime equal to P2, that is the rotation is done, translation is done, and then multiplied by the scaling matrix equal to S. Do the back substitution, you will get P2 equal to P1 plus matrix T multiplied by S. And for P1 you have to carry out P multiplied by R. So we have P into R plus we have translation matrix, and then again you have to multiply by scaling matrix. And we'll see a difficulty why this product is not carried out. So the size of the matrix P is, rotation matrix is 2 by 2 and the translation matrix is 1 by 2 and the scaling matrix is 2 by 2. Now check the inner product here. We have 2 and 2. It means that this matrix size will be 1 by 2 and we have to add here 1 by 2. For addition, both matrices must be of same size. So to carry out this matrix product, by combining all the transformation into resultant transformation system, a homogeneous coordinate system is used. That is, we want to discuss here the homogeneous coordinate system. In this system point, the 2D space is represented by 3D coordinate along the x, y and on imaginary axis. So every point of the coordinate P, x and y can be represented in a matrix form. So instead of using the two-dimensional, we'll introduce here the three-dimensional, which is called as the homogeneous coordinate system, which is representing the x-axis, y-axis and one imaginary axis, so that every point P, x, y can be represented as P, x, y and W. In that case, we have P prime will be represented as x prime, y prime, W prime. Now here W represent a parameter which describes the class of transformation. So in a homogeneous coordinate system, the point in 2D space is represented by three coordinates along the x-axis, y-axis and on imaginary axis. So every point having the coordinate P, x, y can be represented in the matrix form as P, x, y, W, and the new point coordinate is represented as x prime, y prime, W prime. That is, the transform point is represented by x prime, y prime, W prime. Here W represents a parameter which defines the class of transformation, and the representation of a point in a matrix as shown above is called as homogeneous coordinate. As the transformation are carried out in 2D space, the coordinate on imaginary axis does not change. Hence we have W prime is same as equal to W. Also the transformation two-dimensional nature, value of W does not affect the transformation. Hence for the sake of simplicity, coordinate of imaginary axis is taken as 1. So there is no role of imaginary axis. Just for simplicity of a calculation, we are providing here the third coordinate as the imaginary axis, so we can take that value for quick calculation is equal to 1. Previously we have scaling matrix is only 2 by 2. This time we have introduced here one additional imaginary coordinate. So we have x prime, y prime and W is replaced by 1, will be equal to xy1. We know that x prime is same as equal to x into sx. So we have x into sx, y into 0, 1 into 0 will give the same result. Similarly, we have y prime will be equal to y multiplied by sy. So we have x multiplied by 0, y multiplied by sy, 1 multiplied by 0, you will get sy. And the last coordinate we have 1, x into 0, y into 0, 1 into 1. So we can do this scaling matrix, and hence we have three-dimensional scaling matrix is represented by sx 0, 0, 0, sy 0, 0, 0, 1. Now check the matrix size here. We have 1 row and 3 columns. So we have size is 1 by 3. This size is also 1 by 3. This size is 3 by 3. So 3 and 3 cancel, we get 1 by 3. Now this one is representing the rotation matrix. Already we know here the value of x prime during the rotation is given as x multiplied by cos theta minus y multiplied by sin theta, and we have y prime will be given as x into sin theta plus y multiplied by cos theta. So we have x prime, y prime 1, x, y 1. So this matrix size is again 1 by 3. This matrix size is again 1 by 3. We have x into cos theta minus y into sin theta and 1 into 0. So we can generate x prime. Then we have x into sin theta, y into cos theta, plus we have 1 into 0, and finally we have 1, 1. X into 0, y into 0, 1 into 1 is 1. So this one is representing the rotation matrix in 3 dimension. And the size of this matrix is 3 by 3. Again 3 and 3 will cancel out, we will get here 1 by 3. So procedure is more simplified if we use the homogeneous coordinate system. And for translation matrix, so whenever we carry out translation, in that case we have x prime is equal to x plus tx. We have y prime is equal to y plus ty. So you have to carefully write down the matrix T. This time we have x into 1 is same as x, y into 0 is 0, 1 into tx, that is x plus tx. Secondly, we have y prime is equal to x into 0, y into 1 plus 1 into ty, and last coordinate will generate same as equal to 1. So this one is the standard translation matrix we have to use, which one is 3 by 3. In this fashion we have defined the 3 matrices in a homogeneous system. One is the scaling, second is the rotation, and third is the translation. So remember this matrix. So based on rotation, scaling and translation, we'll take here the first numerical, in which determine the resultant transformation matrix to rotate a point by an angle theta about an arbitrary point C, xc, yc. So we have given here one point and you want to rotate that point about the point C. So let's say we have point P is xy and we want to rotate this point about C. This point C has x coordinate equal to xc and the y coordinate is equal to yc by an angle equal to theta. So this point P will shift to the new position and we want to find out the new position if it is shifted by an angle theta, which is anticlockwise, and we are interested to know the point P prime, which has a coordinate of x prime and y prime. If you recall the rotation of a point, in that case we have developed the matrix of rotation as cos theta sin theta minus sin theta cos theta for 2-dimensional, but this rotation is carried out about the origin, and this matrix is defined only if we have a rotation about the point O, that is the origin. In the present case here, the point C is not at origin but is away from origin. So first you have to shift the point C to point O by using the translation matrix, and you have to do the translation Tx is equal to minus xc and ty is equal to minus yc. In that case, the point C will shift to point O. So you have to use the number of steps here. The first step is that the point C you have to shift to the origin. In that case, we have to use the translation along the y direction is minus yc, and then translation along the x direction equal to minus xc. Translate the point C to the origin using tx is equal to minus of xc and ty is equal to minus of yc. The translation matrix is given as 1 0 0 0 1 0 tx ty 1. So in that case, we get a translation matrix as 1 0 0 1 0 0. Then we have 0 1 0 0 1 0. Then we have tx equal to minus xc, ty is equal to minus yc, and we have 1. So this is first translation. Then we have to rotate the point about O. Then you have to rotate the point P about the point C, which is now at origin. But since the translation is done, the point P has new coordinate is x1, y1. So at the given position, we have to rotate it by an angle equal to theta in a counterclockwise direction. So if you rotate it by an angle equal to theta, the point will shift to the new position. Let's say the point P is shift to the new position is equal to x2, y2. And the angle turn in anticlockwise sense equal to theta. So we have to use the rotation matrix cos theta sin theta 0 minus sin theta cos theta 0 0 0 1. So same matrix will write here as a rotation matrix R equal to cos theta, then we have sin theta, then we have 0, then we have minus of sin theta, then we have cos theta 0, and the last row we have 0 0 1. This step is compulsory because the rotation matrix will only perform the rotation about the origin. Now finally we want the point C back to the xc and yc coordinates. So you have to do again the translation by tx equal to xc and ty is equal to yc. So finally the point C will come back to the original position and we'll get the same figure as the original figure. So finally we'll get here the point P prime, which has a x coordinate equal to x prime and y coordinate equal to y prime. So the third step is to translate the point C from origin using the translation along the x-axis equal to xc, along the y direction equal to yc. In that case, the second translation matrix will be 1 0 0 0 1 0. Instead of minus xc, it will be plus xc. Instead of minus yc, it will be plus yc, and 1 is same. So three steps are required here. First, translate the point C to the origin, then carry out the rotation about the origin, and then revert the point C to the original position. So the product of T1 multiplied by R multiplied by T2 will change the position of point P to P prime. So in this case, the resultant transition matrix, that is the total transition matrix, is consist of T1 multiplied by rotation matrix R multiplied by second translation matrix equal to T2. All these matrices are 3 by 3, so this product is possible. So we have resultant transition matrix is represented by TT. We'll replace here T1, then R, and then by T2 matrix. So we have total transformation matrix is 1 0 0 0 1 0 minus xc yc 1, same as T1. Then we have cos theta sin theta 0 minus sin theta cos theta 0 0 0 1. Then we have 1 0 0 0 1 0. Then we have xc yc into 1. So we'll carry out the from outer side. So first matrix will remain as it is. So you have to do the product of rotation matrix with translation matrix T2. So we have cos of theta into 1 is same as cos theta. Sin theta into 0 is 0. 0 into x is 0. Then we have cos theta into 0 is 0. Sin theta into 1 is plus sin theta. 0 into yc is 0. Then we have cos theta into 0 is 0. Sin theta into 0 is 0. 0 into 1 is 0. Then we have minus sin theta into 1 is minus sin theta. Cos theta into 0 is 0. Then we have 0 into xc is 0. Then we have minus sin theta into 0 is 0. Cos theta into 1 is plus cos theta. 0 into yc is 0. Minus sin theta into 0 is 0. Cos theta into 0 is 0. And 0 into 1 is 0. Now the third row. So we have 0 into 1 is 0. 0 into 0 is equal to 0. We have 1 into xc. So we have plus xc. Then we have 0 into 0 is 0. 0 into 1 is 0. 1 into yc. So plus yc. 0 into 0 is 0. 0 into 0 is 0. 1 into 1 is plus 1. So we left here cos theta, then minus sin theta xc, sin theta cos theta yc, and 0, 0, 1. So we have resultant transition matrix is T1, which is not changed, is 1, 0, 0, 0, 1, 0, minus xc minus yc 1. First term here is a cos theta. So we have cos of theta. Second element is minus sin theta. So we have minus of sin theta. And then we have xc. In the second column we have sin theta. So we have sin theta. Then we have cos theta. And then we have yc. And in final column we have 0, 0, 1. Now you have to do the product of T1 and the resultant of rotation plus second translation matrix. In that case we have resultant transition matrix TT is equal to the first row and first column. We have 1 into cos theta is cos theta. Then we have 0 into sin theta is 0. Then we have 0 into xc is 0. Then first row, second column, we have 1 into sin theta is sin theta. 0 into cos theta is 0. 0 into yc is 0. Then we have first row and third column. So we have 1 into 0 is 0. 0 into 0 is plus 0. And 0 into 1 is plus 0. Now we'll go for second row, first column. So we have 0 into cos theta is 0. 1 into minus sin theta is minus sin theta. 0 into xc is 0. Then we have second row and second column. So 0 into sin theta is 0. 1 into cos theta is plus cos theta. 0 into yc is plus 0. Then we have second row and third column. So we have 0 into 0 is 0. 1 into 0 is 0. 0 into 1 is again 0. Finally, we have third row and first column. So we have minus xc into cos theta minus xc into cos theta minus yc and minus sin theta. That will be equal to plus yc sin theta. So we have plus yc into sin theta. And finally we have 1 into xc is plus xc. Then we have third row and the second column. So we have minus xc into sin theta is minus xc into sin theta. Then we have minus yc into cos theta is minus yc into cos theta. And we have 1 into yc is plus yc. Then finally we have third row and third column. Minus xc into 0 is 0. minus yc into 0 is 0 and 1 into 1 is 1. So this one is representing the total transformation matrix. So finally we'll get here cos theta term. So this term I will just clean up here. Then we'll get minus sin theta, and in the third row and the first column we have minus xc cos theta plus yc sin theta plus xc. Then we have second column we have sin theta term present there. Then this 0 we have to remove and this 0 is removed. So we have cos theta minus xc sin theta minus yc cos theta plus yc. All this term has 0, so we only 1 0 is left. Here also 1 0 is left, and finally we are left here with 1. So this one is our final answer. The video you are watching is from the app, which is the Mohod class app available on Google Store, and in this app we'll cover all subjects involved in mechanical engineering for GATE. Join the course directly from your mobile. The link is given here.